Colligative properties. Colligative properties are properties of the solution that depend only on the amount of solute present in the solution, not on what the solute happens to be. There are four major colligative properties. They are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Three are strongly related to each other: vapor pressure lowering, boiling point elevation, and freezing point depression, while the fourth is independent of the other three. In introducing these properties, we will consider solutions that have a non-volatile solute, that is, a solute without a significant vapor pressure, like an ionic solid. Things are a bit different with a volatile solute, but a discussion of that topic is beyond the scope of this course. Vapor pressure lowering results from the fact that there are forces between the solute and solvent, forces that may limit the ability of a solvent molecule to escape from the solution. The vapor pressure of a solution is lower than the vapor pressure of the pure solvent. Raoult's law is the mathematical relationship that relates the vapor pressure of the solution to the vapor pressure of the pure solvent. In the equation, P sub A is the vapor pressure of the solution. X sub A is the mole fraction of component A. P0 sub A is the vapor pressure of the pure component A, pure solvent. This is one of those times when you want to make sure that you have the vapor pressure of the solvent. There is one problem on using Raoult's law on the problem sheet for this lesson. Boiling point elevation and freezing point depression. In this diagram, we have both the phase diagram of the pure solvent, in this case water, shown by the black lines, and the phase diagram of the solution, shown with blue lines. Note that the solution is only a solution in the liquid phase, not in the gas phase, because the solute is non-volatile, and not in the solid phase. If frozen slowly enough, the solid is pure water ice. Because the vapor pressure of the solution is lower than the vapor pressure of the pure solvent, that will raise the temperature we must reach to get the liquid to boil. Since the triple point is the temperature and pressure at which the vapor pressure of the solid and liquid are equal, if the solution has a lower vapor pressure, then the triple point of the solution is at a lower temperature, and that will lower the freezing point of the solution. Strictly speaking, since the change in vapor pressure is proportional to the change in the boiling point, the change in the boiling point is proportional to the mole fraction of the solute. However, if there is relatively little of the solute present, a not uncommon situation, then the mole fraction is proportional to the molality. So the change in a boiling point is proportional to the molality of the solute in the solution, a relationship shown mathematically by this equation. Delta T sub B, the change in the boiling point, is equal to K sub B, the boiling point elevation constant for the solvent, times the molality of the solute. Since the boiling point was raised, we add this change to the normal boiling point of the solvent. In a similar way, we can find the change in the freezing point of the solution using this equation. Delta T sub F, the change in the freezing point, is equal to K sub F, the freezing point depression constant for the solvent, times the molality of the solute. Since the freezing point is being lowered, we subtract this change from the normal freezing point of the solvent. The table you have seen includes the normal boiling point and freezing point of several substances and their boiling point elevation constants and freezing point depression constants. You will note the similarity of these two equations. You should also note that in neither case does the identity of the solute enter into the calculation, only how much of the solute is present. It turns out that there is a relationship among the enthalpy for a phase change, the entropy for the change, and the temperature at which the change occurs. We will look at enthalpy and entropy more closely later in the course, but here the enthalpy change equals the temperature at which the change occurs times the entropy change. The top line is the entropy of the vapor of the solvent, and the bottom line is the entropy of the solid solvent. Somewhere in the middle is the entropy of the liquid solvent. The dotted line shows the change in entropy for the freezing of the solvent, labeled delta S sub FUS for fusion. And the solid line shows the entropy change for the boiling of the solvent, labeled delta S sub VAP for vaporization. The boiling point can be calculated from the heat of vaporization, delta H VAP, and the entropy change, delta S VAP. Similarly, the freezing point can be calculated from the heat of fusion, delta H FUS, and the entropy change, delta S FUS. What happens when we have a solution? The vapor of the solution is only the solvent vapor, so the entropy is the same as for the pure solvent. Similarly, the entropy of the solid phase is the same because it is the pure solvent. However, the solution has greater entropy than the pure solvent. What is the effect of this? The change in entropy for the liquid vaporizing is less for the solution than it is for the pure solvent. The value of the heat of vaporization does not change from the pure solvent to the solution, since the same process is occurring in each case. So the same value of delta H is equal to T times a smaller value of delta S. Therefore, T must be larger. The boiling point rises. What happens with freezing? In this case, the entropy change for the solution is greater than the change for the pure solvent. Again, the value of the heat of fusion is the same for the solution as it is for the pure solvent. So the same value of delta H is equal to T times a larger value of delta S. So the value of T must be smaller. The freezing point decreases. When an electrolyte, like an ionic solid, dissolves in water, the compound breaks into ions. The colligative properties depend on the number of independent particles present, so solutions of electrolytes should show greater changes than the solutions of non-electrolytes. In fact, they do. But a 1 molar solution of sodium chloride, which breaks into 2 ions, does not show twice the effect of a 1 molar solution of methanol, for example. The reason that the salt does not have twice the effect is that the ions are not completely separated from each other. Rather, depending on the concentration of the solution, some ions reassociate for a short time, decreasing the number of independent particles in the solution. The table shows the ratio of the measured particle concentration to the actual concentration for sucrose and 3 salts, which form 2, 3, and 2 ions. Note that the ratio is 1 for sucrose, which does not dissociate. For the 3 ionic solids, the ratio increases as the concentrations decrease, approaching the limiting value of the number of ions produced. The lower the concentration, the less likely the ions are to be close enough to reassociate. Therefore, the less the effect, and the closer the Van 't Hoff factor is to the ideal value. So the number of particles is dependent on the concentration. You might think about the fact that the change for MgSO4 is different from the change for NaCl, significantly so. To take into account the effect of the dissociation of electrolytes, we modify the previous equations by multiplying by the Van 't Hoff factor I. The equation becomes delta T equals K times M times I. For our purposes, we will be using the limiting values. That is, the number of particles the compound breaks up into. Note that the 3 electrolytes given here are strong electrolytes, which dissociate completely. For weak electrolytes, the number of particles is between 1 and the dissociated number, which is usually 2, because they do not completely dissociate. There are 3 problems using the boiling point elevation and freezing point depression and the Van 't Hoff factor on the problem sheet for this lesson. Osmosis is a very important property in biological systems. When we have a semi-permeable membrane, large molecules cannot pass through the membrane, but small molecules can. Most cell membranes are semi-permeable membranes, which allow water to pass through, but do not allow solutes to pass through.
When a solution of higher concentration and a solution of lower concentration are separated by a semi-permeable membrane, one through which solvent molecules can pass but through which solute particles cannot, solvent molecules will pass through the membrane from the side containing the more dilute solution to the side containing the more concentrated solution. This process is called osmosis. Solvent molecules actually move through the membrane in both directions, but because the concentration of the solvent is higher on the right, solvent molecules on the right collide with the membrane more frequently than on the left, resulting in a net flow of solvent from right to left. If we apply pressure to the side containing the more concentrated solution, we can slow or stop the flow of solvent. This is due to the fact that more solvent molecules in the concentrated solution are colliding with the membrane, since the pressure or force per unit area is increasing. The precise amount of pressure necessary to stop the flow of solvent is called the osmotic pressure. A pressure greater than the osmotic pressure will cause solvent molecules to flow from the more concentrated solution to the more dilute solution. This process is called reverse osmosis.
As the video showed, the molecules of water pass through the membrane in both directions. However, since the concentration of water molecules is higher on the side with a lower concentration of solute, the water will flow from the side with a lower solute concentration to the side with a higher solute concentration. The osmotic pressure, symbol pi, is calculated using the equation shown on this slide. Pi equals m times r times t, where m is the molarity of the particles in the solution, r is the gas constant, and T is the Kelvin temperature. An isotonic solution for a cell is a solution that has the same concentration of solutes as there are inside the cell. The water will flow in and out through the membrane equally. If the concentration outside the cell is higher, then the solution is hypertonic. water flows out of the cell in a process called crenation. If the concentrations are different enough, the cell dehydrates, killing the cell. If the concentration outside the cell is lower, the solution is hypotonic. Water flows into the cell in a process called hemolysis. If enough water flows in, the membrane can burst, killing the cell.